Electromagnetic spectrum, light and energy. What is light? I asked this question before in the classroom. We said that light is electromagnetic radiation, travels as a wave, and it's composed of particles. A particle of light is called a photon, and photon has special characteristics. It's a massless particle. It does have momentum. It can be affected by gravity, and in a vacuum, it travels at about 3 times 10 to the 8th meters per second, which is the cosmic speed limit of the universe. So we talked about waves before, a little bit of review of waves, right? How high the wave goes up, that's the amplitude, and one complete cycle, that's going to be the wavelength. So um, in a light wave, the amplitude, in visible light, the amplitude is going to be the brightness. Waves have wavelength and frequency. They're reciprocals of each other. In visible light, the frequency determines the color. And, we talked about the Doppler effect and the sound that race cars make when they're coming towards you and going away from you. And light does the same thing as well. There's Doppler effect in light, and objects moving away from us seem a little bit more red. Objects moving towards us seem a little bit more blue. Of course, they have to go at really fast speeds for us to notice that color shift. And we also talked about the speed of a wave. Velocity is equal to frequency times wavelength. And we said it was the medium that determines the speed of a wave. So waves in different mediums travel different speeds. Invisible light is the same thing. It travels the fastest in a vacuum, and then it travels different speeds in different mediums. So, for example, water is slower than a vacuum, and then diamond is slower than water. And here's a picture of this electromagnetic spectrum. So all electromagnetic radiation is the same thing. You've got visible light in the middle. Off to the left, you have very dangerous things, high frequency, dangerous things like gamma rays and X rays. And then off to the right, you have safer things, um, infrared, microwave, and radio waves. So things to the right have a low frequency and they have really long wavelengths. So you can see 1 meter for a wavelength there to the right, and then to the right of that, you can see 10,000 meters or 1,000 meters. And so those waves are giant, right? 1,000 meters is a kilometer, which is half a mile. But then going to the left, at gamma rays, we have 10 to the negative fifth nanometers. So first of all, a nanometer is really, really small. It's times 10 to the negative ninth. And then we're going even smaller than that, times 10 to the negative fifth. So together, those are going to be times 10 to the negative 14th. So really, really small wavelengths. Looking at the frequencies on the right, radio waves, we have these really low frequencies, 1,000 hertz. Then we get towards visible light, and then it's times 10 to the 14th, so 14 zeros. And then we get all the way to the gamma rays, the frequency is really high, times 10 to the 24th, so that's 24 zeros. So to the left is more energy, more dangerous, higher frequency. To the right is less energy, lower frequency. So if we're looking at visible light, what has more energy, blue or red? Well, blue is to the left, so blue has more energy. And the speed of light, as we said, is about 3 times 10 to the 8th meters per second. And the number shown here, 299 million, is more precise, but we just round it to 3 times 10 to the 8th meters per second. And this is the speed of light in a vacuum. So when we talked about Snell's law, we talked about the index of refraction. Here's the formula again. The index of refraction, n, is equal to the speed of light in a vacuum divided by the speed of light in that medium. So c is going to be 3 times 10 to the 8th, and v is going to be whatever the speed of light is in that particular substance. And we come up with n, the index of refraction. So the chart to the right shows the index of refraction for a bunch of different materials: air, water, diamond, and so on. And we did the Snell's Law lab, and that phenomenon is called refraction of light. So just a little bit of review. The picture to the right here on the top has vacuum, and on the bottom has a medium. So, very similar vacuum and air. Light's going a very similar speed, so we could pretend this is air and water. So I have the light coming in, and that's called the incident ray. There's then the angle of incidence, which is the angle between the incident ray and the normal. Then the ray enters into the medium, and the light gets deflected. In this case, the medium is more dense than the vacuum, so the ray gets refracted and deflected towards the normal. So I have in the medium, I have the refracted ray and the angle of refraction. And remember that the formula here was n1 sine theta 1 equals n2 sine theta 2. Another property of light and waves in general is diffraction. Diffraction is the bending of waves around an object. So the picture on the left have these wave crests, these wave fronts coming in, crests and troughs. All of a sudden they get to a barrier with a small slit or a wall with a hole, and then as the medium moves past that barrier, the waves now start to curl around. Diffraction, direction change of waves as they pass through a hole. But it doesn't have to be a slit or a hole, it could just be an object. So the picture to the right shows these waves coming, and there's that object in the way, and then you can see that the waves are now curved because of that object. So the bending of light around an object is called diffraction, and light does this as well. A quick review of wave interference. When two waves line up, that's called in phase. So I have the blue and orange waves. All the crests and troughs are lining up, and so those waves are perfectly in phase. So that's constructive interference. The resultant wave is adding the amplitudes together. On the right, the orange and blue waves are 180 degrees out of phase or perfectly out of phase. And so a crest lines up with the trough and so on. So those waves are going to cancel out. That's destructive interference. Now I'm subtracting the amplitudes. And in this case, they're two identical waves perfectly out of phase. So those two waves are going to cancel each other to be nothing. And one of the ways in which we prove that light is a wave is the double slit experiment. And just two pictures of the same thing here. Light waves come in, they go through a barrier with two slits in it. The light is then diffracted, and then the light from those two slits causes a pattern, an interference pattern of light and dark, proving that light must be a wave because we have constructive and destructive interference. So now we get two new formulas. E is equal to HF, and E is equal to HC over lambda. So this is telling us that the energy of a photon is proportional to its frequency. Or the second formula, E is equal to hc over lambda, is saying that the speed of light, or the energy of a photon, is equal to and proportional to the speed of light divided by the wavelength. So h is something called Planck's constant, 6.63 times 10 to the negative 34 joule seconds. That's the number for h. To the negative 34 means this is a really, really, really small number, meaning that the energy of one photon is really going to be a very small number. F is the frequency of the photon, which is the frequency of electromagnetic radiation. C is the speed of light in a vacuum, 3 times 10 to the 8th meters per second. And lambda is the wavelength of the photon. So two ways in which we can find the energy. If we know the frequency, we're going to say E is equal to HF. If we know the wavelength, we're going to say E is equal to HC divided by lambda. Just a reminder that the relationship between frequency and period. So 1 over period is frequency, 1 over frequency is period. So the first formula, T is equal to 1 over F. Period is 1 over frequency. I could rewrite that as F is equal to 1 over T. And then on the bottom, usually I write the formula for speed of a wave as V is equal to F lambda. And that's the same thing as V is equal to lambda divided by T. Or the way it's being shown here, the period is equal to the wavelength divided by the velocity. And for the speed of light, I could just put C in place of V, and then when I'm doing the actual calculations, I put in 3 times 10 to the 8th meters per second. And lastly, I just want to talk about how electromagnetic waves are made, and we can talk specifically about radio waves. So the text says, an antenna at the left has alternating current, which is electrons, which is charges, which oscillate back and forth in the wire, accelerating and decelerating. And it creates electromagnetic waves shown by the changing magnetic field, the B field, and the electric field, the E field. So to the left here is this wire, and the little wave symbol is telling us that there's AC or alternating current in that wire. So you have to picture it. The electrons are moving up and down in the wire real fast. They're reversing direction. So they're accelerating. They accelerate up, come to a stop, and they accelerate down, come to a stop, accelerate up, and back and forth, oscillating in the wire. And because these charges are accelerating and decelerating, they create an electric field and a magnetic field, which is changing. So if you think back to electric fields, anytime I have a charge, there's an electric field around that charge. And when that charge is moving, that electric field is changing, and so it creates a wave. And so that's the blue wave here. The blue wave here is representing the change in an electric field. And the E means electric field, and that vertical plane is showing us that the change is in that plane, like in the Y direction. And also, when a charge moves, it creates a magnetic field. Remember the PowerPoint about magnets? Moving charges create magnetic fields. So the moving charges in the wire are creating a magnetic field, and because the charges are speeding up and slowing down, that magnetic field is changing. So a magnetic field is also called a B field. So the red wave is representing a magnetic field which is changing. And the B plane is showing us that that's moving like along the x-axis. And so those two together create an electromagnetic wave. So in the case of a radio, you oscillate the electrons in the wire with a very specific frequency, and then it creates an electromagnetic wave with a very specific frequency. And that's how radio waves are made. Okay, so that's it for this PowerPoint, and please watch the videos that I have up there, and please complete the worksheet, and later in the week I will show my solutions to the worksheet, and then later in the week we'll also have a quiz.